Okay, part six, floating point numbers. So we talked about integers before, whole numbers. Floating point numbers are any numbers with a fractional component. Now, as you might imagine, it is actually not trivial to represent an arbitrary number with an arbitrary fraction at an arbitrary magnitude, whether big or small, with high precision in a finite number of ones and zeros. Most computers that do this implement the IEEE floating point specification, which defines how to represent these numbers using ones and zeros. And most CPUs have a floating point unit embedded in the CPU that does floating point arithmetic, and a lot of that hardware will have a floating point representation that is defined in hardware to be 64 to 80 bits long. So these don't behave like integers in Python, where like they can grow to arbitrarily large uh, uh, values. But you'll see you can represent um, enormous values using this definition. I have linked here a video that gets is really quite an excellent video. If you listen to it, you might want to reduce the speed because it goes quite fast. But if you're curious about how this standard actually works, this video is the best one I have found that sort of walks through the compromises that they had to make to design this standard for representing numbers. Um, I don't want to belabor a lot of these points because they really are not super important or really important at all for being able to program at the level that most people do. Like, I very rarely in the course of my job have to think about, oh, is this some quirk of how floating point numbers are represented in a computer that is at play here? Uh, I I have I do walk through some of the consequences of some of the design decisions in the floating point standard down here for you, but I'm not going to belabor this point either. I would recommend you kind of go through and read through here. If you don't follow super closely, no big deal, but just know that what's going on with floating point numbers is that for many numbers we can't actually represent them exactly. Um, we can we can represent a number that is closer to the number we're trying to represent than any other number that we can represent in floating point. This means that floating point numbers are always inherently a little bit imprecise, but usually that imprecision is at a magnitude that we are unconcerned with. Um, this means that comparisons between floating points using exact comparisons are usually not advisable. You probably want to do like compare a float to another float within some tolerance, some very small tolerance that you might be interested in. Um, but there are also cases, and I give one example here, where the imprecision of a float can cause your math to blow up. Um, this will probably never happen to you, but it is possible, and be aware of it. But really, the tension that is going on here with floating point numbers is that suppose you have a very large number, like I think down here, what are one of the ones I use, like um, e to the 300, like a very large number. it is hard, well, really impossible given this format, to represent the highest magnitude part of this number very precisely, as well as extremely small values. So if you have an extremely big number, to hold that bigness, you are sacrificing some precision in the smaller part of that number. Whereas if you have a very, very small number, you can represent much more precision at the very small end of the spectrum. Watch this video up here if you want that to make sense. Okay, so, well, let's just look at this real quick. We're not going to go through all of this. I'll leave this as an exercise to you to just kind of read through. But, floats, like integers, you can assign them to memory addresses. Most oftentimes in literal form, they'll just be, decimal numbers written like this. You can also write them in literal form using scientific notation. And I have an assertion here that is showing that all of these are equivalent ways to represent the same number. This last one is not a literal, this is an expression because we're using operators. This is exponents, we're saying 10 to the 2. Floats will implicitly convert to booleans when you use logical operators on them, just like integers. And then the rest of this, I leave this as an exercise to go through. So after you go through this and you kind of get that, what's going on, go ahead and proceed to the gateway exercises. And I'll see you there.